Alrighty, hello everybody, welcome back. Today we're just gonna be talking and discussing about hurricanes and how they form, why they're important, and how we can prepare for them. With hurricane season starting, and our first named storm just occurring today on Tuesday, June 24th, as recording, I think it's important that it's good to understand how hurricanes are, how they form, and stuff like that. So we're going to be starting off from Miami, right? So that's going to be the National Weather Service's location for tracking and monitoring hurricanes over the Atlantic Basin. And as you can see on this map here, here's kind of where they look, right? So you can kind of see how they start from thunderstorms all the way until, they unfortunately reach the Caribbean, go through the Gulf or the East Coast, and do sometimes affect us. And that's what we're trying to prevent here. Okay, so what is the biggest driving force of all weather or pretty much everything on Earth? It's the sun, right? So the sun's energy is what pretty much drives all of these rain systems, is what drives our weather, is what drives the atmosphere to move. Um, so as you can see here, that of course changes throughout the seasons, how much sun energy we receive due to our tilt in our orbit around the sun. Right, so you can kind of see during the winter, that's when we receive the least amount of sunlight, and during the summer, we receive the most amount of sunlight, right? The most amount of sun rays in a given area at a given time. And that's kind of visualized here in this kind of visual. You can kind of see during the summer months, during June in the northern hemisphere, there's a lot more of of those sun rays hitting in a certain area, right? Compared to December in the winter in the northern hemisphere, where you can see there's a lot kind of there's still the same amount of sun rays in a sense, but because of our tilt, right, and our position in the orbit of the Earth around the sun, those sun rays kind of have to bend a little bit to reach us, right? Because the Earth is a sphere. And directly due to that, we receive less energy from the sun, which directly means that we receive less heat, which is why our seasons change. Alright, so that's all fine. But what does that truly mean for our hurricanes? Well, here's another big step or a big factor into how hurricanes form and how our weather works pretty much. And that's going to be the Coriolis effect as visualized here on this map. Right? So pretty much the thing that drives the Coriolis effect, the thing that drives a lot of our weather is also the rotation of the earth, right? The earth rotates once every 24 hours, which means that there is some sort of velocity or movement throughout the earth, right? So as you can see, compared to the equator, the poles don't have to move that much to make a full rotation compared to the poles, right? Because the poles, there's a lot more distance it has to travel in that 24 hours, right? Which is also why our Earth has an elliptical shape with a bit of a bulge around the equator. That's because there's so much mass there. There's so much to move around the Earth in that rotation. And that also plays an effect in our atmosphere and our winds. So the black lines you see there is pretty much the movement of the air, pretty much winds at the surface. And you can see there on the left, those red and blue lines um, represent the air movement in the atmosphere. So you can see that red with the heat, right? Heat from the sun is that air kind of rising, right? It sinks first, goes on the surface where all the heat is absorbed from the sun, most of it, and then rises at some point, which you can see here is at the equator, right? And you can see again happens at the 6-degree line of latitude. Further visualized in this map here, you can kind of see how our systems change and move through each line's latitude. You can see how they're mirrored from the northern hemisphere to the southern hemisphere, right? So we have our trade winds in the lower latitudes that all converge at the equatorial low, which is where again the air is moving the quickest around the Earth, or just moving the quickest as the Earth rotates every 24 hours. And what happens there is the Earth rises, right? Because of course there is also where it's receiving a lot of solar radiation, and of course that heat causes heat rises, so that air that's superheated rises, right? And there's a lot more tropical activity there. There's a lot more rain. There's a lot more, just movement. So you can see that's where the equatorial low or ITCZ is, or intertropical convergence zone. Pretty much that's where a lot of our storms happen around the equator. But moving from that latitude wise, from 0 to 30, we have our trade winds, right? Our easterlies. And those are winds just moving from the east as the Earth rotates, and they converge around the equatorial low and rise with the heat of the air. Moving from that, we have our 30-degree line. That's when, give or take, on average, where our subtropical high rather, will be. Right, so that's pretty much signifies. We'll get into that in just a moment. Sinking air, calmer conditions, etc., etc. Moving from that, we have our westerlies, winds coming from the west, and then we have our subpolar low, right? Again, that signifies kind of rising air. And then moving from that, we have our easterlies and our polar high, right? Because the air is not moving that much relative to the equator, right? That's why during the winter or the summer, rather, we have full 24-hour daylight, right? The sun never sets in the poles during, again, during the summer months, which on each pole is the opposite end of the year. And that will signify that the sun literally rotates around the earth, which is what it looks like to us relative to us. But of course, we know now that we are the ones rotating, and the sun is just kind of moving as we rotate relative to us. Okay, that's cool and all, but what do all those H and L's mean? We mentioned that before, but we just said that L means rising air and maybe rain. H means sinking air, calmer conditions. What could that possibly mean? Let's get right into that. Alrighty, so high pressure and low pressure. What is it? So low pressure is that air kind of converging, as you can see, and then rising, right? And that air holds a lot of heat. It can hold a lot of moisture from lakes, from streams, from oceans, from even the soil and trees transpirating, etc., etc. And as all of that air begins to rise, it cools, right? There's less pressure higher up in the atmosphere, just because of gravity. So as there's less air molecules there, right, it expands. And as something expands, it cools. As it cools, that water vapor and all the other particles in there begin to condense, right? Namely, just the water vapor condenses, which is what forms the clouds, right? Of course, as those clouds get heavier and heavier and more dense, then you can begin rain, and that's how low pressure systems work. That's how they create rain, and so on and so forth. You can kind of see how the air kind of moves from high pressure to low pressure, right? At high pressure, of course, where a lot more air is going to be. That's where it's a lot more dense. And so that's why the air flows from high pressure to low pressure. That's a big driver of winds as well, are these high and low pressure areas. So you can kind of see how it moves high up in the atmosphere, right? And they all converge again to form a high pressure zone as all the air, now devoid of moisture, devoid of all of that, now begins to converge once again because it's heavier than the air around it and sinks, right? And as it sinks, it gains pressure, right? And of course, closer to the surface, there's just going to be more temperature because of how the air, how the ground absorbs more of that sunlight. And as it gains temperature, as it begins to condense because of the higher air pressure, it now gains heat. And so that's how we have our low pressure areas. And again, with the high pressure areas, they're not carrying any moisture, right? The air is sinking, it disperses all that water vapor and moisture. So we don't have that high level of, or that high chance of precipitation. You might still have humidity, right? It's a lower chance, but there still could be humidity during the summer months, etc., etc. But generally, low pressure, rising air, stormy conditions, high pressure, convergent air, but divergent on the surface, and sinking. So you can see here, those high and low pressure systems or areas change from the northern and southern hemisphere. Again, they're just mirrored. So low pressure northern hemisphere signifies counterclockwise air. The air is moving, the wind are moving counterclockwise relative to the system, and as they converge, again, they rise, right? And that's usually the winds coming from the high pressure, which is the sinking air, and they move clockwise. And then the northern hemisphere. In the southern hemisphere, again, it's mirrored. It's the complete opposite. And you can see kind of here that kind of dome or ridging effect from the high pressure zone. You can see as it sinks, it gains more pressure, it gains more heat, and it kind of spins clockwise around the center. And then the low pressure, again, those ones moving from high to low, that low pressure they start to spin anti-clockwise, counterclockwise, and begin to rise with the heat and all the water vapor that it holds, which is why we have a higher chance for storms. Why the wind, there's usually a lot more winds as the low pressure system is advancing and is approaching, um, and all the other conditions that come with it as well. All right, quick break, quick recap. So, we've learned three big things so far that all drive our weather. First, we learned about our seasons, right? We learned how in the northern hemisphere, summer means more sun rays in the northern hemisphere. In the winter, it's the complete opposite. Spring and fall is where it's about average, right? We get about 12-hour days, so we get about equal sun rays across the earth, right? That's where the sun is shining on the equator during the spring and fall equinox. We also learned about the Coriolis effect. We learned that the spin of the earth causes that air to move, right, and move at different speeds or rates, because, of course, the equator is moving a lot more distance to make a full rotation than the poles. And we also learned about high and low pressure systems, right? We learned about how high pressure systems signify sinking air, right, towards the surface and divergent from the surface, right? And on the surface, it's going to be higher pressure because there's just more air molecules in that given space. And they're moving towards the low pressure systems, which is that convergent air, right? As it spins counterclockwise in the northern hemisphere, right? And of course, you know that the high pressure spins clockwise in the northern hemisphere. Southern hemisphere, it spins anti-clockwise, so counterclockwise for high pressure, and so on and so forth. But in the low pressure, right, in the northern hemisphere that spins counterclockwise, we learn that that air converges and rises, right? And as it rises, it brings up water vapor and everything else from the surface. Um, that's airborne at least, and then it cools and condenses as it expands up in the atmosphere, which causes our rain. So, what does this have to do with hurricanes? Well, let's find out. So, this map will be showing us how our intertropical convergence zone, which again referencing the Coriolis map, that's kind of our equator zone where the convergence of the storms happen, kind of shows us how it moves throughout the year. Because, of course, that main direct line of sunlight moves as the seasons progress. So, you can see in July, in the summer in the northern hemisphere, that line is a bit more north, that red line there, right? You can see how it moves as it progresses through the earth, right? And in January, it's going to be our winter months in the northern hemisphere, summer in the southern hemisphere. You can see how it shifts south, right? So it kind of goes kind of through Indonesia, right? Through a bit southern, more southern part of Africa, and then kind of comes back up very close to the red line there. So you can see it kind of goes to a similar part in the Atlantic, but it's kind of a different direction as it converges just a little bit through Brazil and then diverges again as it enters into the Pacific. But then the question still remains, if all the storms converge there, how do we still have storms in the US? How do these hurricanes impact us if they're just thunderstorms that happen from the ITZZ? Well, guess we'd have to look at how they progress. So let's get started. So shown here is a weather radar map of Africa during July. So it's going to be the summer month ITZZ. You can see how the storms kind of bubble up during the heat of the day on that ITZZ, right, and move in a westerly direction, right, coming from the east, um, on that kind of a little bit north of the equator, right? You can kind of see how they move through that kind of very just south of the Sahara, off the coast into the Atlantic, right? So that's what causes those storms. That's where those thunderstorms come from. But how do they go from just a little thunderstorm here that looks rather harmless, if I'm being honest, there's some rain, right? But then how do they stay alive over the Atlantic and become these massive, devastating hurricanes for us, right? Because that didn't look too bad. Well, shown here is the global cyclone track across the entire globe. So, of course, we can see it's not just Africa we're worried about here. It's more that line there, that intertropical convergence zone. We can kind of see where those thunderstorms originate and come from and how they're able to build with all that ocean moisture and heat content to these massive systems. You can see the color kind of says their intensity. So you can see they always start, rather calm, but then they enter an area of the Atlantic, they enter this warm water zone, whatever it may be, that causes them to explode, right? You can see it even happens in the southern hemisphere too, right? A little bit away from the equator as well. And we all kind of seem to move away from the equator in that same respect. They can be in the Pacific, the Indian Ocean, or the Atlantic, which again are all low pressure systems, right? Again, that rising air, that convergent air, that all cause the rain, the wind, the storms, the events that happen when a hurricane happens. So let's look a bit closer into our Atlantic Basin, where we're starting from here. We can really see how those storms kind of follow a very familiar track, right? They kind of start from that little area, they traverse across the Atlantic, and then they kind of always seem to bend in some way. They can either bend in the Gulf, right, and go through the center of the U.S., or they can miss the U.S. entirely and just bend in the middle of the Atlantic, which we always hope to happen. Just hopefully it doesn't bend too much and reaches, as you can see here, these extratropical system, which is the gray again. Color shows intensity. Those bright colors show high intensity. Those kind of lower colors, green and blue, are just like depression and tropical storm, which aren't too devastating. Usually, tropical storm can be devastating, especially with rainfall. And then the gray means extratropical, which means that it's lost its tropical characteristics. It's not really a tropical or hurricane, tropical storm or a hurricane rather. It's just kind of like like a little sea storm in a sense. But we hope it doesn't reach to Europe or any other areas as well, because it can cause damage. So the main reason these storms bend is due to what's called the Bermuda High, which is this big ridge of high pressure, usually in the summer months, that expands over a large part of the northern Atlantic, right? And what usually happens with low pressure systems is they like to kind of tug around the edge of high pressure ridges. So you can kind of see if the ridge is a stronger high, right, and it's a more expansive, reaches the U.S. eastern seaboard, those storms might bend kind of closer to the Caribbean, right, and may even enter into the Yucatan and the Gulf, which may affect one of our Gulf states. If it's a little bit less strong or a little bit close, a little bit further to the east, those might be that might signify an eastern seaboard storm if a tropical disturbance comes up. But if it's kind of a weaker high, a smaller ridge and further off to the east, then the storm can end up remaining just a fish storm, which is what we call storms that stay off in the Atlantic or just stay off in the ocean, right? It may still affect ships and little islands like Bermuda, right? And hopefully it doesn't, but for the most part, in terms of the mainland, in the U.S. and stuff like that, we remain relatively safe compared to if it was a stronger Bermuda high. So now we have a pretty good understanding of how hurricanes form, why they even or how they can even form, right? All the ingredients that kind of plays into it and stuff like that. Because again, these storms are starting out as thunderstorms, right? Once they reach the open water and the water temperature is sufficient, right? All they need is 26, 27 Celsius or 80 degrees Fahrenheit. That kind of opens up the door for them to receive the energy content as well as the moisture and just pretty much all the ingredients necessary to produce these big hurricanes, right? And again, these are low pressure systems, so this air is rising, it's spinning, it's creating the winds and stuff like that as well, right? And you can see here, this is a forecast for Hurricane Irma for the National Hurricane Center, right? And you can see this is supposed to make landfall, and this the sad part about this, those M's mean this is a major storm, right? And these things they cause damage, but thanks to our advancements in technology and knowledge into this with radar and other technologies, we're able to better understand exactly how these systems work, what they are, and all the stuff that comes with them, right? So hopefully this video helps you become better aware and prepared for this 2025 hurricane season as it unfortunately begins. So you guys are able to, not see these storms and be like, oh, dude, why does this keep happening? This must be some bad luck. No, it is a part of nature, but with more preparedness and more knowledge, we can mitigate the effects and the disastrous, uh, uh, you know, things that happen from these hurricanes as climate change, unfortunately changes the way these storms behave in some respects. Hope you guys have a great rest of your evening. This next video will just be a little bit of a look into the hurricane season in 2018 in September and October. And then beyond that, it'll be up to you to see how this hurricane season fares. So, best of luck. Love you all and have a great rest of your day.